Look up at the night sky tonight, really look, and you'll see more than just stars. You'll see a vast, living laboratory where the universe itself is conducting experiments on scales we're only beginning to understand. Every flicker of light, every shadow between the constellations holds clues to mysteries that could rewrite the textbooks of science. This is the power of the cosmos. It doesn't just inspire awe, it pushes humanity forward, challenging us to ask bigger questions and dream bolder dreams. Welcome to Celestial Secrets Revealed, where we explore how the universe isn't just a backdrop to human ingenuity. It's the driving force behind some of the most groundbreaking discoveries of our time. Think about the last time you stood outside under a clear, starry sky. That feeling of smallness, of wonder, it's not just poetic. It's the same spark that has driven astronomers, physicists, and explorers for centuries. From Galileo's first telescope to the jaw-dropping images from the James Webb Space Telescope, every glimpse into the cosmos has reshaped our understanding of reality. But here's what's truly thrilling. We're living in an era where those revelations are coming faster than ever. Dark matter, exoplanets with potential for life, black holes bending the fabric of space-time. These aren't just concepts from sci-fi. They're real, they're being studied right now, and they're opening doors to technologies and ideas that could transform our future. So what does it mean for us, for humanity, to live in a time when the universe feels both more knowable and more mysterious than ever? That's the journey we're about to take together. Over the next few minutes, we'll travel from the mind-bending frontiers of theoretical physics to the cutting-edge tools scientists are using to decode the cosmos. You'll see how the stars aren't just distant lights but active players in a story that's still being written, one where we get to be the explorers. This isn't just about space, it's about how the universe challenges us to think bigger, dig deeper, and reimagine what's possible. Ready to uncover the celestial secrets shaping tomorrow's science? Let's begin. The universe isn't just a place to explore, it's the ultimate testing ground, a colossal laboratory where nature runs experiments we could never dream of replicating here on Earth. Picture this: down here, gravity holds everything in place, temperatures are relatively mild, and the environment is stable. But out there, the cosmos serves up conditions so extreme, they bend the rules of physics as we know them. Take neutron stars, for example. These incredibly dense remnants of exploded stars pack more mass than our Sun into a city-sized sphere. The gravity on their surface is so intense, it warps space-time itself, giving scientists a real-world test bed for Einstein's theory of relativity. Then there's the eerie silence of deep space, a perfect vacuum where particles are few and far between. This emptiness isn't just empty, it's a stage for quantum mechanics to play out in ways that baffle even the brightest minds. Particles pop in and out of existence, entangled across vast distances, defying classical logic. On Earth, we struggle to isolate quantum effects because our environment is too noisy. But in space, the universe strips away the interference, letting researchers observe these strange phenomena in their purest form. And let's not forget cosmic rays, high-energy particles racing across the galaxy at nearly the speed of light. These aren't just random space radiation, they're messengers carrying secrets about the most violent events in the universe, like supernova and black hole jets. By studying them, scientists can probe the limits of particle physics, uncovering clues about how matter behaves under conditions no Earth-bound lab could ever recreate. But perhaps the most mind-bending experiments happen near black holes, where gravity is so strong that not even light can escape. These cosmic monsters don't just swallow matter, They twist space and time into knots, creating environments where the laws of physics as we know them start to break down. By observing how matter behaves at the edge of a black hole, researchers are testing theories that could one day unite quantum mechanics and relativity, two pillars of modern physics that still refuse to play nicely together. The beauty of all this, the cosmos doesn't just pose the big questions, it hands us the tools to answer them. Every flicker of a distant star, every ripple in space-time, every unexplained signal from the void is a piece of the puzzle. And as we gather those pieces, we're not just learning about the universe, we're rewriting the rules of science itself. Now consider this: if space is such a perfect laboratory, why is one of its biggest experiments still eluding us? Dark matter, the invisible glue holding galaxies together, remains one of the most tantalizing mysteries in modern astrophysics. We can't see it, we can't touch it, yet we know it's there, shaping the cosmos in ways we're only beginning to grasp. Dark matter is the universe's greatest disappearing act, a ghost that leaves footprints everywhere but refuses to show its face. Think of it like this: if the cosmos were a grand play, dark matter would be the invisible stagehand, silently pulling the strings behind the scenes. We know it's there because galaxies spin faster than they should, their outer stars whirling at speeds that defy the laws of gravity as we understand them. Without dark matter's gravitational grip, these galaxies would simply fly apart. Yet, despite making up over 1/4 of the universe's total mass, it doesn't emit, absorb, or reflect light. It's the ultimate cosmic hide-and-seek champion. So how do you study something you can't see? Scientists have gotten creative. One approach is gravitational lensing, a phenomenon where the gravity of dark matter bends light from distant galaxies, warping their images like a funhouse mirror. These distortions act as cosmic fingerprints, revealing where dark matter lurks. Another clue comes from the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light map out where dark matter clumped together in the early universe, seeding the vast web of galaxies we see today. But what is it? The leading theories range from weakly interacting massive particles, or WIMP hypothetical heavy particles that barely interact with normal matter, to actions, ultra-light particles that could flow through space like an invisible river. Then there's the wild card: maybe dark matter isn't a particle at all. Some physicists suggest we've got gravity all wrong, and what we're seeing is evidence of a deeper, undiscovered law of nature. To crack the case, experiments are running everywhere from abandoned gold mines to the icy expanse of Antarctica. Deep underground, detectors sit in pristine silence, waiting for the rare moment a dark matter particle might bump into an atom. In space, telescopes like the Euclid mission are mapping the universe in unprecedented detail, tracing dark matter's shadowy scaffolding. The stakes couldn't be higher. If dark matter is a new particle, it could open doors to a whole new realm of physics beyond the standard model, our current rulebook for how particles behave. If it's something else entirely, we might need to rewrite that rulebook from scratch. Either way, the hunt for dark matter isn't just about filling in a gap in our knowledge. It's about uncovering the hidden architecture of reality itself. And yet, as mysterious as dark matter is, it's only half the story. Lurking in the void is something even more elusive: dark energy, the force accelerating the universe's expansion at an ever-increasing pace. But that's a revelation for another moment. For now, let's sit with the awe of this. We're surrounded by an invisible ocean of matter, shaping everything we see, and we're just beginning to learn its language. If dark matter is the invisible hand shaping the cosmos, dark energy is the breath blowing it apart. This mysterious force isn't just expanding the universe, it's accelerating that expansion, pushing galaxies away from each other faster and faster with every passing moment. Imagine inflating a balloon, but instead of slowing down as it grows, the rubber stretches quicker over time. That's the unsettling reality astronomers stumbled upon in 1998, when observations of distant supernova revealed the universe wasn't just growing, it was speeding up. What makes dark energy so baffling is how little we understand it. Unlike dark matter, which clumps around galaxies, dark energy seems to be woven into the fabric of space itself, a uniform pressure acting everywhere at once. Einstein once proposed a similar idea, his cosmological constant, but later dismissed it as his greatest blunder. Now it turns out he might have been onto something after all. Except here's the twist, the numbers don't add up. Quantum physics predicts a vacuum energy that could explain dark energy, but the calculated value is off by a staggering 120 orders of magnitude. That's like expecting a single drop of water and instead facing an ocean larger than the observable universe. So what else could it be? Some theorists suggest dark energy might be evidence of a fifth fundamental force, one that only makes its presence known across vast cosmic distances. Others propose it's a dynamic field, like an invisible fluid filling space, its properties evolving over time. Then there's the radical idea that our understanding of gravity itself is incomplete, that Einstein's equations need rewriting on the grandest scales. Projects like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are racing to untangle this enigma. By mapping millions of galaxies and measuring how their light bends and dims, scientists hope to trace dark energy's influence across billions of years. The stakes, nothing less than the ultimate fate of the cosmos. If dark energy keeps strengthening, it could tear apart everything: galaxies, stars, even atoms, in a distant future called the Big Rip. Or it might fade away, allowing gravity to pull the universe back together in a big crunch. But the deepest mystery lies in the past. How does dark energy connect to cosmic inflation? That explosive moment when the universe ballooned from smaller than an atom to cosmic size in a fraction of a second. Both phenomena suggest space itself has an innate energy, a hidden driver behind existence. Unlocking that link could reveal why the universe exists at all and what lies beyond the horizon of our expanding reality. For now, dark energy remains the universe's most profound question mark, a reminder that the greatest discoveries often begin with the humblest admission: we don't know. Picture the universe in its first moments not just expanding, but exploding outward faster than the speed of light. This wasn't just growth, it was a cosmic growth spurt so extreme, it stretched a speck of space smaller than an atom to the size of a grapefruit in less than a trillionth of a second. Scientists call this inflation, and it's the only theory that explains why the universe looks so eerily uniform in every direction. Without it, the cosmos would be a patchwork of wildly different temperatures and densities. Instead, the afterglow of the Big Bang, the cosmic microwave background, reveals a near-perfect symmetry, as if someone ironed out the wrinkles of space-time itself. But here's the puzzle: what flicked the switch? What force could have unleashed such a violent, precise expansion? The leading suspect is a quantum field, a kind of energy that permeated the early universe, acting like an anti-gravity engine. As this field decayed, it released a flood of particles and radiation, setting the stage for everything we see today. The echoes of that moment might still be ringing through the cosmos in the form of primordial gravitational waves, ripples in space-time so faint they've eluded detection for decades. That's where experiments like BICEP and the Laser Interferometer Gravitational Wave Observatory, or LIGO, come in. By scanning the cosmic microwave background for telltale swirls or listening for the faintest tremors in space-time, scientists hope to catch inflation red-handed. A confirmed detection wouldn't just fill in a blank in our cosmic origin story. It could bridge the gap between quantum mechanics and Einstein's general relativity, two theories that have stubbornly refused to reconcile. And the implications go even deeper. If inflation happened once, could it happen again? Some theories suggest our universe might be just one bubble in an endless cosmic foam, with other universes inflating beyond our reach, each with its own laws of physics. It's a dizzying thought. The Big Bang might not have been the beginning but a reboot in an infinite cycle. Yet for all its grandeur, inflation left behind fingerprints we're only now learning to read. The distribution of galaxies, the slight unevenness in the cosmic microwave background, these are relics of quantum fluctuations stretched to cosmic scales during that explosive moment. In a very real sense, the largest structures in the universe were seeded by the tiniest trembles of reality. Now, shift your gaze from the birth of the cosmos to its most enigmatic destroyers, black holes. These aren't just cosmic vacuum cleaners, they're time capsules, holding secrets about the universe's most extreme environments. Just as the Rosetta Stone unlocked ancient languages, black holes could decipher the deepest laws of physics. At the edge of a black hole, gravity doesn't just bend space-time, it ties it in knots. Matter gets stretched into spaghetti-like strands, temperatures soar to billions of degrees, and the very concept of time warps. It's here, in this chaos, that scientists are testing whether Einstein's theory of relativity holds up, or if it crumbles, revealing a deeper truth. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, it wasn't just a triumph of technology. It was a direct glimpse into the heart of darkness, where physics as we know it reaches its limits. But black holes aren't just destructive, they're also cosmic powerhouses, spewing jets of energy that can outshine entire galaxies. These jets are particle accelerators on a universal scale, forging elements and shaping the evolution of galaxies around them. Even Hawking radiation, the faint glow predicted to leak from black holes, hints at a quantum connection between gravity and the subatomic world. What makes black holes such perfect laboratories is their simplicity. Unlike stars or planets, which have complex structures and compositions, a black hole is defined by just three things: mass, spin, and charge. This purity makes them ideal for probing fundamental questions. For instance, do they truly erase information, violating quantum mechanics, or does that information linger, encoded in ways we haven't yet imagined? The answer could rewrite our understanding of reality itself. From the universe's explosive infancy to the quiet, devouring darkness of black holes, one thing is clear: the cosmos doesn't just hide its secrets, it dares us to uncover them. And with each revelation, we're not just observers of the universe, we're participants in its grandest experiment. Black holes aren't just cosmic oddities, they're the ultimate paradox machines, bending the rules of physics until they snap. Take the information paradox, a puzzle that stumped scientists for decades. When matter falls into a black hole, it vanishes from our universe, seemingly erased forever. But quantum mechanics insists information can't be destroyed. It must persist somehow, even if scrambled beyond recognition. Stephen Hawking's groundbreaking work added fuel to the fire. His theory of Hawking radiation suggests black holes slowly leak energy, shrinking over eons until they vanish. But if the hole disappears, what happens to all that swallowed information? Does it leak back out, encoded in the radiation, or is it lost forever, violating one of quantum theory's sacred principles? This isn't just academic wrestling. The answer could crack open the door to a theory of everything, a framework uniting Einstein's gravity with the quantum realm. Some physicists propose wild solutions, like holographic universes where information isn't lost but projected onto the black hole's event horizon like a cosmic movie screen. Others suggest black holes birth baby universes, exporting the information to another reality. Then there's the firewall hypothesis, where the event horizon might be a searing wall of energy, shredding anything that crosses. Each idea pushes our understanding to the brink, revealing how black holes aren't just objects, they're mirrors reflecting the limits of human knowledge. The Event Horizon Telescope's iconic image of the M87 black hole wasn't just a triumph of engineering. That glowing ring of light, warped by gravity's grip, confirmed Einstein's predictions with stunning precision. Yet, lurking in the shadows of that achievement are unanswered questions. Why do some black holes, like Sagittarius, a star at our galaxy's heart, flicker unpredictably? What causes their jets, streams of plasma racing near light speed, to flare and dim? These aren't just quirks, they're clues about how black holes interact with their surroundings, bending space-time like a whirlpool distorts water. Now, imagine an object even denser than a black hole, where matter is packed so tightly it defies logic. Neutron stars are what you'd get if you crushed a sun into a city-sized sphere, where a single teaspoon of material would weigh 1 billion tons on Earth. These stellar corpses spin faster than blender blades, some rotating hundreds of times per second, their surfaces rippling with mountains just millimeters high yet strong enough to warp space-time. When two neutron stars collide, the fireworks are spectacular. These collisions forge gold, platinum, and other heavy elements in their wake, literally raining precious metals across the cosmos. But neutron stars aren't just cosmic alchemists. Their interiors may harbor matter in states so extreme they don't exist anywhere else in the universe. Quark-gluon plasma, hyperons, even strange matter that could infect ordinary atoms like a sci-fi virus. These are the bizarre possibilities physicists are probing. By studying the gravitational waves from neutron star mergers detected by observatories like LIGO, we're glimpsing the behavior of matter under pressures so intense they recreate conditions from the universe's first microseconds. From black holes that erase information to neutron stars spinning faster than kitchen blenders, these cosmic extremes aren't just curiosities. They're the universe's way of stress testing our theories, pushing us to think beyond textbooks. And with every mystery solved, another, deeper question emerges because the cosmos doesn't give up its secrets easily. It dares us to dig deeper. Neutron stars are nature's ultimate pressure cookers, stellar corpses so dense they cram the mass of an entire sun into a sphere no wider than Manhattan. Picture scooping up a single teaspoon of their material. That tiny amount would weigh more than 1 billion tons here on Earth, collapsing under its own gravity the moment it touched our planet. These extreme objects are born from the ashes of supernova, where dying stars shed their outer layers in violent explosions, leaving behind cores so compressed that atoms themselves collapse. Electrons and protons fuse into neutrons, packing together until the star becomes one giant atomic nucleus, a city-sized ball of pure nuclear matter. But the real magic happens beneath their crusts. Deep inside a neutron star, conditions resemble the universe just milliseconds after the Big Bang, a seething ocean of quarks and gluons, the fundamental building blocks of protons and neutrons. Under pressures 100 trillion times greater than Earth's core, these particles might break free, forming exotic states of matter like quark soup or strange matter, a hypothetical substance so stable it could convert anything it touches. Some theories even suggest neutron stars could harbor tiny, dense quark stars at their centers, hidden gems wrapped in layers of ultra-compressed neutrons. Then there's the way these cosmic powerhouses interact with the universe around them. Neutron stars spin at mind-bending speeds, some rotating hundreds of times per second, their magnetic fields trillions of times stronger than Earth. These pulsars, rapidly spinning neutron stars, emit beams of radiation that sweep across space like lighthouse beams. When one of these beams points toward Earth, we detect it as a precise pulse, a cosmic metronome keeping time with jaw-dropping accuracy. In fact, the first exoplanets ever discovered were found orbiting a pulsar, their presence revealed by subtle wobbles in the star's clockwork pulses. But neutron stars don't just tick quietly in the dark. When two of them collide, the universe puts on a show. These mergers send ripples through space-time gravitational waves we can now detect with observatories like LIGO. The aftermath is even more spectacular. The collision spews out a glowing cloud of heavy elements, forging gold, platinum, and uranium in quantities that dwarf Earth's entire reserves. Every piece of jewelry, every microchip containing gold, it likely originated in the fiery wreckage of neutron stars crashing together billions of years ago. What's truly astonishing is how much we've learned from these distant, hyper-dense objects. By studying their pulses, scientists have tested Einstein's theory of relativity with precision impossible in any Earth lab. The way their gravity bends light, the way their spins slow over time, each observation peels back another layer of the universe's deepest laws. Yet for all we've uncovered, neutron stars still guard their most tantalizing secrets. Could their cores contain stable quark matter, a form of material that defies everything we know about atomic structure? Might they even give rise to strangelets, hypothetical particles that could rewrite the rules of nuclear physics? The answers could be hiding in the next gravitational wave signal, the next flicker of a pulsar's beam. And just as neutron stars push the limits of matter, exoplanet discoveries stretch our understanding of where and how life might arise. From diamond planets to molten lava worlds, the universe keeps proving it's far stranger, far more inventive than we ever imagined. The hunt for worlds beyond our solar system has turned up treasures beyond imagination, planets where diamonds rain from the sky, where molten lava oceans stretch endlessly under blood-red skies, and where water might exist in quantities dwarfing all of Earth's oceans combined. Since the first exoplanet discovery in 1992, astronomers have catalogued over 5,000 of these alien worlds, each one rewriting the rulebook on what a planet can be. Take Kepler-16b, for example, a world orbiting two suns just like Luke Skywalker's Tatooine, where double sunsets paint the horizon, or WASP-76b, a scorching giant where daytime temperatures vaporize iron, only for it to condense and rain down as molten metal at night. What makes these discoveries revolutionary isn't just their strangeness, it's what they reveal about our place in the cosmos. For centuries, we assumed our solar system was the blueprint. Now we know it's just one variation in a galactic symphony of planetary systems. Some stars host hot Jupiters, gas giants orbiting closer to their stars than Mercury does to our Sun. Others have super-Earths, rocky planets up to 10 times more massive than ours, possibly with thick hydrogen atmospheres or deep global oceans. Then there are rogue planets drifting through interstellar space without a star to call home, their surfaces frozen in eternal darkness. The Holy Grail, of course, is finding an Earth twin, a rocky planet in the habitable zone, where liquid water could pool on the surface. NASA Kepler telescope revealed thousands of candidates, but it's the James Webb Space Telescope that's changing the game. By analyzing starlight filtering through exoplanet atmospheres, JWST can detect chemical fingerprints, oxygen, methane, even potential signs of industrial pollution. In 2023, it spotted carbon dioxide and water vapor in the atmosphere of K218b, a super-Earth 120 light-years away. The discovery sparked excitement because where there's water and carbon, the ingredients for life as we know it aren't far behind. But how do these exotic worlds form? The process starts in swirling disks of gas and dust around young stars, where particles clump together like cosmic snowballs. In our solar system, Jupiter's gravity likely shaped Earth's destiny by hurling icy material inward, delivering water to our planet. Around other stars, different gravitational dances produce radically different outcomes. Some systems have planets orbiting in perfect circles, others in wild, stretched ellipses. A few even have planets spinning backward compared to their star's rotation, evidence of violent past collisions or close encounters with passing stars. The diversity raises profound questions. Could life emerge on a tidally locked planet, where one side always faces its star in perpetual daylight while the other freezes in eternal night? What about worlds orbiting red dwarfs bathed in frequent stellar flares? Each discovery expands the boundaries of what we consider habitable. Now, shift your gaze from planetary surfaces to the invisible particles racing between them. Cosmic rays, high-energy protons and atomic nuclei traveling at nearly light speed, are the universe's bullet trains carrying secrets about supernova, black holes, and the most violent events in the cosmos. When these particles slam into Earth's atmosphere, they create cascades of secondary particles, some reaching the ground. But their journey began millions of years ago, accelerated by shock waves from exploding stars or the intense magnetic fields around black holes. By studying their composition and energy, scientists can reconstruct their origins like cosmic detectives piecing together a crime scene. What makes cosmic rays so valuable is that they're natural particle accelerators, reaching energies far beyond what we can achieve in labs like CERN. Some ultra-high-energy cosmic rays pack the punch of a fast-pitched baseball, all in a single subatomic particle. Where these extreme particles come from remains one of astrophysics' great puzzles. Theories range from active galactic nuclei, supermassive black holes devouring matter, to rare, starburst galaxies where stars form at frenzied rates. The search for answers isn't just academic. Cosmic rays affect everything from satellite electronics to astronaut health, and they may have even played a role in Earth's evolutionary history. Some researchers suggest these particles could have triggered mutations that accelerated life's diversification billions of years ago. Now, observatories like the Pierre Auger Array in Argentina are mapping cosmic ray arrival directions, hunting for their sources in the distant universe. From planets where the very concept of weather defies imagination to particles carrying messages from galactic catastrophes, one truth emerges. The universe is far stranger, far more inventive than we ever dreamed. And with each discovery, we're not just mapping the cosmos, we're redefining what's possible. Cosmic rays are like invisible postcards from the most violent corners of the universe. Charged particles racing through space at nearly the speed of light, carrying secrets about supernova, black holes, and events so powerful they defy imagination. Every second, thousands of these particles slam into Earth's atmosphere, triggering showers of secondary particles that rain down on us unnoticed. But don't let their invisibility fool you. These high-energy messengers are anything but ordinary. Some pack the punch of a major league fastball, all concentrated into a single proton. That's energy levels 100 million times greater than anything produced in human-made particle colliders. So where do these cosmic bullets come from? The universe has its own natural accelerators, far more powerful than anything we've built. Supernova exploding stars generate shockwaves that can slingshot particles across galaxies. Active galactic nuclei, where supermassive black holes devour matter, spew jets of plasma capable of accelerating particles to mind-bending speeds. Even merging neutron stars, those dense stellar remnants, might contribute to the cosmic ray zoo. But the real mystery lies with the ultra-high-energy cosmic rays, particles so energetic that their origins remain one of astrophysics' greatest puzzles. These rare giants hit with the force of a falling brick, yet their paths through space are scrambled by magnetic fields, leaving scientists to trace their origins like detectives piecing together a cosmic crime scene. That's where multi-messenger astronomy comes in, a revolutionary approach that combines traditional telescopes with detectors for cosmic rays, neutrinos, and gravitational waves. By cross-referencing these signals, researchers can pinpoint cosmic ray sources with unprecedented precision. Imagine it like triangulating a phone call, but instead of cell towers, you're using exploding stars and colliding black holes as your reference points. In 2017, this method scored a major breakthrough when scientists traced a high-energy neutrino back to a blazar, a supermassive black hole firing a jet directly at Earth. The discovery confirmed what theorists had long suspected. These monstrous black holes are cosmic ray factories, but cosmic rays aren't just astrophysical curiosities. They play a hidden role in our daily lives. When these particles collide with atoms in the upper atmosphere, they create cascades of secondary particles that influence cloud formation, potentially affecting weather patterns and even climate over long timescales. They also pose challenges for astronauts, peppering spacecraft with radiation that could jeopardize long-duration missions to Mars. And here's a wild thought. Some researchers suggest cosmic rays might have played a role in the evolution of life itself, triggering genetic mutations that drove biodiversity. Now, shift your gaze from these high-speed particles to the quantum fabric of the universe itself, a realm where particles flicker in and out of existence, entangled across vast distances, defying logic and intuition. If cosmic rays are the universe's messengers, quantum mechanics is its strangest language, written in probabilities and paradoxes. Quantum mechanics doesn't just defy common sense, it laughs in the face of it. Nowhere is this more apparent than in the vast emptiness of space, where quantum effects play out on cosmic scales. Take entanglement, that eerie phenomenon Einstein called spooky action at a distance. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. On Earth, this seems bizarre enough. But in space, scientists have sent entangled photons hundreds of miles between satellites and ground stations, proving this quantum link holds firm even across distances that would make a classical physicist shudder. Then there's the quantum vacuum, not empty at all, but a seething sea of virtual particles popping in and out of existence. This vacuum energy might seem like an abstract curiosity, but it could hold the key to one of cosmology's biggest mysteries, dark energy. The math suggests the vacuum should be brimming with energy, enough to explain the universe's accelerating expansion. There's just one problem. The numbers are off by a factor of 10 to the power of 120. That's not just a rounding error, it's the biggest mismatch between theory and observation in all of science. This gap is why experiments on the International Space Station are so crucial. In microgravity, scientists can isolate quantum effects from Earth's noisy environment, testing how particles behave when freed from gravity's constant tug. The cold atom lab, for instance, chills atoms to near absolute zero, creating Bose-Einstein condensates, a bizarre state of matter where atoms act as a single quantum wave. These experiments aren't just academic. They're probing whether gravity, the last holdout of classical physics, might have quantum roots after all, which brings us to spacetime itself. Could the fabric of the universe be woven from tiny, discrete quantum threads? Loop quantum gravity and string theory suggest yes, that at the tiniest scales, space-time might be pixelated, like a cosmic digital image. If true, it would mean black holes, wormholes, even the Big Bang are manifestations of a deeper quantum reality. Speaking of wormholes, these theoretical shortcuts through space-time might sound like pure science fiction. But mathematically, they emerge naturally from Einstein's equations as bridges between distant points in the universe. The catch: they'd require exotic matter with negative energy to stay open, something quantum fluctuations might provide if we could harness them. Whether wormholes exist or not, studying them forces us to confront the deepest questions about reality's structure. After all, if space-time can bend, twist, and maybe even tear, what other secrets is the universe keeping? Wormholes exist in the delicate space between mathematical possibility and cosmic reality, bridges through the fabric of space-time so bizarre, they seem ripped from the pages of science fiction. Yet Einstein's general relativity doesn't just allow for their existence, it practically predicts them. Picture space-time as a sheet of paper folded in half. A wormhole would be like poking a pencil through that fold, creating a shortcut between two distant points. The catch: keeping that tunnel stable requires something called exotic matter, a theoretical substance with negative energy density that could counteract gravity's crushing force. So far, no one's found exotic matter, but the search has led to astonishing discoveries. For instance, quantum mechanics hints that the vacuum of space might briefly produce tiny, fleeting wormholes at the subatomic level. These microscopic tunnels could pop in and out of existence like bubbles in a cosmic soda, too small and short-lived to traverse. But their theoretical existence suggests wormholes might not just be cosmic pipe dreams, they could be woven into the fundamental nature of reality. Even if traversable wormholes remain out of reach, studying them has unlocked breakthroughs in physics. The equations describing wormholes overlap with those governing black holes and quantum entanglement, hinting at a deeper connection between gravity and the quantum world. Some researchers propose that entangled particles might be linked by microscopic wormholes, a concept dubbed ER=EPR, merging Einstein's work on wormholes with his skepticism about quantum entanglement. It's a wild idea, but it's pushing theorists to explore how space-time might emerge from the quantum foam at the universe's smallest scales. Then there's the time travel paradox. If wormholes could connect not just space but time, could they create loops where cause and effect break down? The math suggests yes, but nature seems to have safeguards. Quantum effects might pile up at the wormhole's throat, collapsing it before any paradox occurs. Or perhaps the universe simply won't allow time travel, enforcing cosmic consistency in ways we don't yet understand. What's undeniable is how wormholes stretch our imagination. They challenge us to think beyond rockets and light years, to consider that the universe might offer backdoors and shortcuts we've barely begun to map. And while we may never step through a stargate, the pursuit of these cosmic tunnels is already reshaping our understanding of gravity, quantum physics, and the very architecture of reality. Now shift your gaze from the far reaches of space to the technology in your pocket. The same cosmic phenomena that inspire wormhole theories, black holes, neutron stars, the quantum vacuum, are also fueling breakthroughs right here on Earth. From GPS satellites that rely on Einstein's relativity to medical imaging inspired by astrophysics, the universe isn't just out there. It's reshaping our world in ways we're only beginning to appreciate. The technologies we take for granted today often have roots stretching far beyond Earth into the vast expanse of space itself. Consider the GPS guiding your road trips or the smartphone snapping crystal clear photos. Both owe their existence to innovations born from astronomy and space exploration. GPS satellites, for instance, don't just rely on precise clocks. They account for Einstein's theory of relativity, adjusting for time dilation caused by their high-speed orbits. Without these corrections, your navigation would drift off course by miles within minutes. Even the compact camera in your phone traces its lineage to NASA's efforts to miniaturize imaging sensors for space telescopes, proving that the cosmos doesn't just spark curiosity, it fuels tangible breakthroughs. Then there's medical imaging. MRI machines, lifelines of modern diagnostics, harness technology derived from radio astronomy. The same techniques used to map distant galaxies now peer inside the human body, detecting tumors and injuries with pinpoint accuracy. Even the filters purifying your tap water originated from systems designed to recycle fluids aboard spacecraft. It's a reminder that when we push the boundaries of exploration, the benefits ripple back to Earth in unexpected ways. But space's influence goes beyond gadgets and tools. The study of stars has unlocked secrets of nuclear fusion, the process powering our sun. Laboratories worldwide now race to replicate this clean, limitless energy source, inspired by the same celestial engines that have burned for billions of years. Meanwhile, asteroid mining promises to revolutionize resource scarcity. Metals like platinum and rare earth elements, crucial for electronics and green energy, abound in space rocks. Companies already plan robotic missions to extract these materials, potentially turning asteroids into cosmic gas stations for future industries. Yet of all the questions space compels us to ask, none captivates like the search for extraterrestrial intelligence. Projects like SETI scan the skies for radio signals, while new telescopes analyze exoplanet atmospheres for biosignatures, gases like oxygen or methane that could hint at life. The discovery of even microbial aliens would redefine humanity's place in the universe. But the search isn't just about finding others, it's about testing our own limits. Every algorithm developed to sift cosmic noise for artificial patterns, every laser calibrated to detect interstellar messages, sharpens our ability to decode the universe's grandest mysteries. From the tech in your pocket to the energy of tomorrow, the cosmos isn't a distant spectator, it's an active collaborator in human progress. And as we stretch our reach further into the void, the next revolution might not just come from the stars, but from the questions they force us to ask. For decades, the silence of the cosmos has been both a mystery and a motivation. Projects like Breakthrough Listen, the most ambitious search for extraterrestrial intelligence to date, scan the skies with unprecedented precision, analyzing millions of radio frequencies across thousands of nearby stars. Imagine a cosmic eavesdropping operation, sifting through the static of the universe, searching for that one unnatural blip, that telltale pattern screaming, "We are here." So far, the silence persists, but absence of evidence isn't evidence of absence. With over 5,000 exoplanets discovered, many in habitable zones, the sheer statistics tilt the scales toward possibility. The Milky Way alone could harbor billions of Earth-like worlds. If even a fraction developed life, and a fraction of those evolved intelligence, the galaxy should be buzzing with signals. So where is everybody? That question drives scientists to broaden the hunt beyond traditional radio waves. Technosignatures, the fingerprints of advanced civilizations, could take forms we're only beginning to imagine. Picture a distant exoplanet with an atmosphere choked by industrial pollutants like nitrogen dioxide or chlorofluorocarbons. To our telescopes, that chemical imbalance would stand out like a neon sign, betraying the presence of a civilization altering its world. Or consider Dyson spheres, hypothetical megastructures built around stars to harness their energy. These wouldn't just dim a star's light, they'd radiate waste heat at infrared wavelengths, creating a thermal signature unlike any natural object. Even something as mundane as city lights on the night side of an alien world could, in theory, be spotted by next-generation telescopes like the Habitable Worlds Observatory, set to launch in the 2030s. Yet the search isn't just about spotting anomalies. It's about recognizing the difference between nature's randomness and the deliberate marks of intelligence. A pulsar's precise beats once fooled astronomers into dubbing it LGM1 for Little Green Men. Today, machine learning algorithms pass petabytes of data, flagging anything that defies natural explanations. The challenge: the universe is full of phenomena that mimic artificial signals. Quasars, masers, even colliding neutron stars can masquerade as alien broadcasts. This brings us to the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and the utter lack of contact. One unsettling explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. Maybe complex life is rarer than we think, or perhaps civilizations inevitably self-destruct before they can colonize the stars. Alternatively, we might be searching the wrong way. Advanced societies could have moved beyond radio, communicating via neutrino beams or quantum entanglement technologies we're only beginning to fathom. Then there's the zoo hypothesis, the idea that extraterrestrials deliberately avoid contact, observing us like animals in a cosmic preserve. Or worse, we're the ants at their picnic, too primitive to notice. Whatever the answer, the search itself reshapes humanity's perspective. Every scan of the heavens, every analysis of exoplanet atmospheres isn't just about finding aliens. It's about understanding our place in a universe that grows stranger and more wondrous with every discovery. And if the silence continues, that too speaks volumes. In a cosmos where even emptiness tells a story, the absence of signals might be the most profound message of all. The Fermi Paradox is more than just a scientific question. It's a mirror held up to humanity, forcing us to confront our deepest assumptions about life in the universe. On paper, the numbers seem undeniable. With hundreds of billions of stars in our galaxy alone, many hosting planets in habitable zones, the cosmos should be buzzing with civilizations. Yet the silence is deafening. This contradiction has spawned theories ranging from the unsettling to the downright existential. Take the Great Filter hypothesis. It suggests that somewhere between the emergence of life and interstellar colonization, there's a near insurmountable barrier, a cosmic checkpoint that wipes out civilizations before they can spread. The terrifying possibility: we might not have passed it yet. Climate collapse, nuclear war, runaway AI, any could be the filter that silences civilizations like ours before they leave their cradle. But not all explanations are so grim. Another possibility is that advanced civilizations operate on scales we can't perceive. Imagine ants at a picnic, oblivious to the conversations happening above them. To a Type 3 civilization harnessing the energy of entire galaxies, our radio signals might be as insignificant as background static. Or consider the zoo hypothesis, the idea that Earth is intentionally left undisturbed, a protected wildlife reserve in a galactic conservation program. We wouldn't notice the observers any more than a fish notices the glass walls of its tank. Then there's the darker twist that the universe is inherently hostile to intelligent life. Gamma-ray bursts, supervolcanoes, or even predatory AI from older civilizations could systematically prune budding species before they become threats or competitors. It's a cosmic version of the dark forest theory, where civilizations stay hidden to survive. Yet the paradox also pushes us to question our methods. Are we searching for the right things? Our hunt for radio signals assumes aliens communicate as we did in the 20th century, but a civilization just a few thousand years ahead might use neutrino beams or quantum entanglement, technologies we're only beginning to fathom. Even our concept of life could be hopelessly narrow: silicon-based organisms, plasma beings in stellar atmospheres, or sentient megastructures might thrive in environments we'd consider lethal. All these possibilities lead to one sobering realization: the universe doesn't owe us neighbors. The silence might be telling us that intelligence is rarer or more fragile than we hope. And that makes Earth's survival all the more urgent, because if civilizations routinely vanish before reaching the stars, every day humanity endures is a defiance of cosmic odds. Now consider this: while we search the skies for others, the universe has its own way of reminding us how precarious our existence truly is. From asteroid impacts to solar flares, cosmic threats loom large, and they don't wait for us to solve the Fermi Paradox before striking. The universe may inspire wonder, but it also harbors dangers capable of resetting life's clock in an instant. 66 million years ago, a 6-mile-wide asteroid struck Earth with the force of 1 billion nuclear bombs, triggering wildfires, acid rain, and a years-long winter that erased 75% of all species, including the dinosaurs. Today, telescopes like Pan-STARRS in Hawaii scan the skies nightly, cataloging near-Earth objects that could follow in that asteroid's footsteps. The good news: NASA's DART mission proved we can nudge a threatening asteroid off course. In 2022, the spacecraft intentionally crashed into the moonlet Dimorphos, altering its orbit and marking humanity's first successful planetary defense test. The bad news: thousands of potentially hazardous asteroids remain undiscovered, some as dark as charcoal and nearly invisible until they're alarmingly close. But asteroids aren't the only celestial hazards. Our sun, the source of life's energy, can also unleash devastating solar storms. In 1859, the Carrington event, a massive coronal mass ejection, fried telegraph wires and sparked auroras as far south as Cuba. A similar storm today could cripple power grids, disable satellites, and knock out global communications for months. The economic toll: estimates suggest up to $2 trillion in damages. That's why agencies like NOAA now monitor solar activity around the clock, giving us precious hours to safeguard critical infrastructure when the sun flares. Then there's the universe's ultimate lightning bolt: gamma-ray bursts. These cosmic explosions, born from collapsing stars or colliding neutron stars, pack more energy in seconds than our sun will emit in its entire lifetime. A nearby burst within 6,000 light-years could strip Earth's ozone layer, bathing the surface in deadly ultraviolet radiation. The Ordovician extinction, which wiped out 85% of marine species 450 million years ago, might have been triggered by just such an event. Fortunately, these bursts are rare in our galactic neighborhood, but their existence is a stark reminder that we inhabit a volatile cosmos where even the stars themselves can turn against us. Understanding these threats isn't about fear, it's about empowerment. Every asteroid tracked, every solar storm predicted, is a step toward resilience in a universe that doesn't guarantee safety. And as we look to the future, these cosmic challenges unite humanity in a shared mission to protect our pale blue dot amidst the stars. Now, rewind the clock further, past the dinosaurs, past the birth of our solar system, to the universe's fiery dawn. The story of how everything began isn't just about the past, it's the key to understanding everything that followed. What if everything we know, every star, every galaxy, even the laws of physics themselves, is just one tiny bubble in an infinite cosmic froth? The multiverse hypothesis isn't science fiction. It's a serious scientific idea that emerges from the edges of cosmology and quantum theory. Picture a vast ocean where each bubble is a separate universe, some with physics like ours, others where gravity might repel or light travels slower than molasses. This isn't just wild speculation, it's a natural extension of cosmic inflation, the theory that our universe underwent exponential expansion in its first moments. If inflation can happen once, why not over and over, birthing countless universes in an endless cascade? String theory adds another layer to this cosmic puzzle. To make the math work, this framework requires at least 10 dimensions, far more than the 4 we experience. The extra dimensions could be curled up, hidden from view, but their configurations might vary across different universes. In some, the forces binding atoms together could be stronger, making stars burn out in a blink. In others, dark energy might dominate so thoroughly that galaxies never form at all. The unsettling implication: our universe's finely tuned constants, the precise strength of gravity, the exact mass of an electron, might not be special. They could just be the lucky numbers we drew in a cosmic lottery. The multiverse idea also reshapes the search for alien life. If countless universes exist, some might harbor civilizations far older and more advanced than ours. Others could be sterile, their physical laws incompatible with even the simplest chemistry. This raises a haunting question: is our universe's apparent fine-tuning for life just a selection effect? We can only exist in a universe that allows life, so of course we'd find ourselves here. Critics argue the multiverse is untestable, more philosophy than science. But researchers are hunting for clues. Some look for bruises in the cosmic microwave background, potential imprints of collisions with other universes. Others simulate how alternate physics might play out in hypothetical sibling universes. And if string theory's extra dimensions are real, future particle accelerators might uncover traces of their influence. What makes the multiverse hypothesis so compelling isn't just its audacity. It's how it forces us to confront the limits of human knowledge. For millennia, we've assumed the universe is all there is. Now we're staring into the abyss of possibility, a reality vaster and stranger than anything we've dared imagine. From the cosmic to the personal, the mysteries of the universe don't just live in telescopes and equations. They echo through human culture, shaping our myths, art, and deepest fears. The stars have always been more than distant lights. They're mirrors reflecting our hopes, dreams, and unanswerable questions about our place in the grand scheme. Long before telescopes pierced the heavens, humanity painted the night sky with stories. Ancient civilizations traced heroes and beasts among the stars, Orion the hunter forever chasing the Pleiades across the firmament, while the Mesopotamians saw a great celestial dragon in the twisting band of the Milky Way. These weren't just imaginative tales, they were humanity's first attempts to make sense of the cosmos, weaving observations of celestial movements into the fabric of daily life. The Egyptians aligned pyramids with Orion's belt, believing the pharaohs would join those stars in the afterlife. Polynesian navigators used star paths like cosmic roadmaps, sailing vast oceans guided by the precise rise and set of constellations. Fast forward to the Renaissance, when Galileo's sketches of the moon's craters blurred the line between science and art. His delicate ink renderings revealed the lunar surface not as a perfect sphere, as Aristotle claimed, but a rugged world with mountains and valleys. This artistic documentation became the foundation of modern astronomy, proof that beauty and discovery often walk hand in hand. Centuries later, Van Gogh's Starry Night captured the turbulent majesty of the cosmos, not through a telescope but through swirling brushstrokes that somehow feel more true than any photograph. That iconic cypress tree reaching toward spiraling stars, It's the human longing for connection with the infinite made visible. Even now, the cosmos ignites creativity in ways that data alone cannot. Film scores swell with otherworldly their means to evoke the vastness of space, while directors use real nebula imagery as backdrops for interstellar epics. Pink Floyd's Dark Side of the Moon syncs with cosmic rhythms, and Bowie's Space Oddity turns orbital isolation into haunting poetry. The James Webb Space Telescope's recent images didn't just advance science, they sparked a new wave of digital art, with creators transforming raw infrared data into dreamscapes of violet and gold. This enduring artistic dialogue reveals something profound. The universe speaks to us in a language beyond equations. Whether etched on cave walls or rendered in pixels, our celestial visions bridge the gap between the quantifiable and the sublime. They remind us that every scientific discovery begins with a spark of wonder, the same awe that made our ancestors gather around fires to tell stories of the stars. Now, shift your gaze from the stars' cultural echoes to time itself, the invisible river flowing through the cosmos. Just as art interprets space, physics deciphers time's elastic nature, where black holes stretch seconds like taffy and light from distant galaxies carries snapshots of the universe's infancy. Time doesn't tick the same way everywhere in the universe. It bends, stretches, and even crawls depending on where you are and how fast you're moving. Einstein's theory of relativity shattered the idea of a universal clock, revealing that time is more like a river, flowing at different speeds depending on the gravitational landscape. Take the astronauts aboard the International Space Station. They're aging just a fraction of a second slower than we are on Earth because they're moving at over 17,000 miles per hour and experiencing weaker gravity. It's not science fiction, it's measurable reality. Even your GPS relies on this cosmic quirk without accounting for time dilation. The fact that satellites' clocks tick faster in orbit than on Earth's surface, your navigation would be off by miles within minutes. But the real mind bender comes when you approach a black hole. Time doesn't just slow down there, it grinds to a near halt from an outsider's perspective. Imagine watching a spaceship fall toward the event horizon. From your vantage point, the ship would appear to freeze, its signals stretching into an infinite redshift. Yet for the crew inside, time would feel normal until the tidal forces, took over. This isn't just theoretical. Astronomers have observed stars orbiting Sagittarius, a star, the supermassive black hole at our galaxy's center, their motions warped by this extreme time warp. So what is time, really? Is it a fundamental fabric of the universe or something that emerges from deeper physics? Quantum gravity theories, like loop quantum gravity or string theory, suggest time might not be a bedrock reality but a side effect, a kind of cosmic illusion arising from the interactions of more basic elements. Some models even propose that at the tiniest scales, time could dissolve entirely, leaving a universe where before and after lose their meaning. Now, stretch your imagination to the universe's ultimate fate. If time is so malleable, how will it end? Will the cosmos keep expanding forever, galaxies flying apart until the last stars burn out and space becomes a cold, dark void? Or could dark energies grip Titan, eventually tearing apart atoms themselves in a big rip? Alternatively, gravity might stage a comeback, pulling everything back into a fiery big crunch, a cosmic reset button. Or perhaps the universe is cyclical, with each big bang birthing a new iteration of reality. The answers might lie in the quantum realm, where the fabric of time itself could unravel into something stranger. Until then, every ticking second reminds us, time isn't just something we measure. It's a dynamic, living part of the cosmos, shaping everything from the orbits of planets to the lifespan of stars. and our own fleeting place in the universe's grand story. The fate of the universe isn't just a philosophical question, it's a race against time to gather the cosmic clues hidden in the light of distant galaxies. Right now, telescopes around the world and in space are scanning the heavens, measuring how fast galaxies are moving apart, how their light bends, and how the large-scale structure of the cosmos evolves. These observations reveal the tug of war between dark energy's relentless push and gravity's stubborn pull. The most precise measurements come from projects like the Dark Energy Survey and the upcoming Euclid Space Telescope, which map the distribution of galaxies across billions of light years. By tracking how galaxy clusters grow and how supernovae dim with distance, scientists can chart the universe's expansion rate over cosmic time. But the real game changer lies in the cosmic microwave background, the faint glow left over from the Big Bang. Tiny fluctuations in this ancient light encode the universe's early composition, offering a snapshot of how much dark energy existed when the cosmos was just 380,000 years old. Combining this with modern observations creates a cosmic timeline showing how dark energy's influence has changed. If it's truly a constant force, as Einstein's cosmological constant suggests, the universe will expand forever, growing colder and emptier until stars burn out and black holes evaporate in a fate called heat death. Yet there's a twist. Some data hints that dark energy might be strengthening over time. If true, it could trigger a big rip, a catastrophic end where the universe's expansion accelerates so violently that it tears apart galaxies, then stars, and finally atoms themselves, shredding the fabric of reality. Alternatively, if dark energy weakens and gravity regains dominance, the cosmos could reverse course in a big crunch, collapsing back into a singularity. The key to unraveling this mystery lies in baryon acoustic oscillations, frozen sound waves from the early universe that left a faint imprint in galaxy distributions. These cosmic fingerprints act as a standard ruler, letting astronomers measure distances across the universe with incredible precision. By comparing these measurements at different epochs, researchers can see if dark energy's push is changing. Meanwhile, gravitational wave astronomy adds another layer to the puzzle. Colliding neutron stars don't just send ripples through space-time, they're cosmic lighthouses. By comparing the gravitational wave signal with the light from these collisions, scientists can independently measure the universe's expansion rate. The result: a tension between different methods that might hint at new physics beyond our current understanding. What makes this search so urgent isn't just academic curiosity. The universe's fate shapes how we understand everything from particle physics to the nature of time itself. If dark energy evolves, it could imply unknown forces or even extra dimensions influencing our cosmos. Each observation, each dataset, is a piece of a puzzle that might reveal whether we're headed toward eternal silence, a fiery collapse, or something even stranger. And while the answers remain elusive, the quest itself transforms how we see our place in the cosmos. Whether the universe ends in ice, fire, or something beyond our imagination, the journey to uncover its secrets is rewriting the story of everything. Telescopes are more than just lenses and mirrors, they're time machines, letting us peer billions of years into the past while revealing the universe's hidden layers. The Hubble Space Telescope, launched in 1990, transformed astronomy by capturing crystal-clear images free from Earth's atmospheric blur. Its iconic snapshot of the Eagle Nebula's pillars of creation, towering clouds of gas where stars are born, didn't just dazzle the public, it rewrote textbooks on stellar formation. Hubble's ultraviolet vision uncovered galaxies forming in the early universe, while its observations of distant supernovae helped discover dark energy. Yet Hubble was only the beginning. Enter the James Webb Space Telescope, or JWST, Hubble's infrared successor. Perched a million miles from Earth, JWST gold-coated beryllium mirrors detect heat signatures from the universe's first galaxies, objects so ancient their light has stretched into infrared wavelengths over 13 billion years. Its early images revealed proto-galaxies clumping together mere moments after the Big Bang, while its spectrographs identified water vapor and organic molecules in exoplanet atmospheres, hints of cosmic ingredients for life. Unlike Hubble, which sees the universe in visible and ultraviolet light, JWST infrared eyes pierce through cosmic dust, unveiling nurseries where stars and planets hide. But not all cosmic secrets are written in light. On Earth's high deserts, radio telescopes like the Atacama Large Millimeter Array, or ALMA, tune into the universe's whisper. These dishes detect millimeter waves radiation emitted by cold gas clouds and nascent planetary systems. ALMA observations of protoplanetary disks, where planets coalesce from dust and ice, have captured baby worlds carving gaps in their stellar cradles. Meanwhile, the Event Horizon Telescope, a global network of radio dishes, made history by imaging a black hole's shadow, proving Einstein's predictions on gravity's grip. Then there are the silent observers buried deep underground. Neutrino telescopes like Japan's Super Kamiok and detect ghostly particles that stream unimpeded from the sun's core or distant supernova. These cosmic messengers reveal processes hidden behind veils of plasma, like the nuclear fusion powering stars or the violent deaths of massive suns. Even more exotic are gravitational wave detectors like LIGO, which hear the ripples from colliding black holes, a symphony of warped space-time. Each tool in astronomy's toolkit unveils a different layer of the cosmos, like translators decoding a celestial language. But the flood of data they produce is overwhelming. That's where artificial intelligence steps in, sifting through noise to find signals no human eye could spot. From classifying galaxies to predicting solar storms, AI is becoming astronomy's indispensable partner. And that's a revolution just beginning. Artificial intelligence isn't just assisting astronomers, it's revolutionizing how we decode the cosmos. Every night, telescopes around the world capture terabytes of data, far more than any team of scientists could analyze in a lifetime. That's where machine learning steps in, sifting through the noise like a cosmic detective. Take the hunt for exoplanets, for example. AI algorithms trained on Kepler Space Telescope data can spot the faintest dips in a star's brightness signatures of distant worlds, with accuracy surpassing human eyes. Some of these programs, like NASA ExoMiner, have discovered hundreds of planets missed by traditional methods, including rocky worlds nestled in habitable zones. But AI's talents don't stop at planet hunting. Classifying galaxies used to require painstaking manual sorting, but neural networks now analyze millions of images in hours, distinguishing spirals from ellipticals or identifying merging galaxies with eerie precision. The same technology even predicts solar storms by recognizing patterns in the sun's magnetic activity, giving satellites and power grids crucial warnings before a coronal mass ejection strikes. The real game changer, AI's ability to find the unexpected. In 2021, researchers fed an algorithm old radio telescope data and stumbled upon mysterious signals that didn't match any known astrophysical source. Dubbed technosignature candidates, these anomalies, while likely natural, show how machine learning can spotlight cosmic oddities humans might overlook. Yet, as AI becomes astronomy's indispensable partner, it raises pressing questions. Who's accountable when an algorithm misclassifies a potentially habitable world? How do we prevent biases in training data from skewing discoveries? And as private companies deploy AI to mine asteroids or stake cosmic claims, who ensures these tools serve humanity collectively, not just a privileged few? This isn't just about efficiency, it's about stewardship. The same algorithms that map asteroids could prioritize targets for mining ventures, risking environmental harm on celestial bodies. The telescopes scanning for alien megastructures might also spot vulnerabilities in rival nation satellites, blurring the line between exploration and surveillance. The ethics of space exploration can't be an afterthought. Every leap in technology demands a parallel leap in responsibility, because the universe isn't just a resource to exploit. It's a shared frontier, and how we navigate it will define not just what we discover, but who we become. Space isn't just the final frontier, it's the next battleground for humanity's most pressing ethical dilemmas. Picture this: a private company lands a robotic miner on an asteroid, extracting platinum worth trillions. Who gets to profit from that haul? The company. The nation that licensed them, or all of humanity? Right now, space law is stuck in the 1960s, governed by treaties like the Outer Space Treaty of 1967, which declares celestial bodies the province of all mankind. But those words were written before corporations had the technology to mine the moon or claim Martian real estate. The result? A legal gray zone where billionaires and nations are racing to set facts on the ground, or rather, in the void. Take Mars as an example. NASA Artemis Accords suggest safety zones around lunar bases, but critics warn this could morph into de facto territorial claims. Should we treat Mars like Antarctica, a scientific preserve free from exploitation? Or will it become another gold rush where the first to plant a flag calls the shots? The risks aren't just theoretical. Imagine a future where lunar water vital for life support and rocket fuel is controlled by a single entity, holding the keys to deeper space exploration hostage. Then there's the specter of space colonialism. History shows what happens when powerful nations exploit new territories without regard for equity or sustainability. Will asteroid mining repeat the mistakes of Earth's resource wars, leaving space littered with environmental damage and inequality? Some propose a common heritage of mankind framework where profits from space resources fund global development. Others argue this stifles innovation, that without the incentive of ownership, companies won't risk billions to mine asteroids. The militarization of space adds another layer of tension. Satellites are already vital for communication, navigation, and surveillance. Nations are testing anti-satellite weapons, creating debris fields that threaten all orbital operations. A single collision could trigger the Kessler syndrome, a cascade of crashes rendering low Earth orbit unusable for generations. Solving these challenges demands more than treaties. It requires a shift in mindset. Just as the International Seabed Authority governs ocean mining beyond national waters, space needs inclusive institutions balancing innovation with stewardship. The alternative, a cosmic Wild West where the powerful stake claims while the rest watch from afar. Now, rewind the clock 13.8 billion years to the moment these questions became possible, the Big Bang. From ethical quandaries to cosmic beginnings, the universe's story is still being written, and humanity's choices today will echo across the ages. The cosmic microwave background isn't just ancient light, it's the universe's baby picture, a snapshot taken when everything was a seething plasma just 380,000 years after the Big Bang. This faint glow, discovered by accident in 1965, holds the secrets of our cosmic origins in its subtle temperature variations. Imagine the entire sky mapped with painstaking precision, revealing patches a few millionths of a degree warmer or cooler than average. These tiny fluctuations are anything but random. They're the cosmic seeds from which galaxies, stars, and planets would eventually grow. Dive deeper into those temperature differences, and you'll find a treasure trove of information. The warmer spots mark regions where matter was slightly denser, their extra gravity pulling in surrounding gas over billions of years. The cooler patches. Those were the cosmic valleys where less matter meant weaker gravitational pull. Over eons, this delicate imbalance sculpted the universe's large-scale structure, weaving the vast cosmic web of filaments and voids we see today. It's like watching a time lapse of a forest growing from scattered seeds, except the seeds were quantum fluctuations, and the forest is the entire observable universe. But the cosmic microwave background has even more to reveal. Hidden within its polarization patterns could be the smoking gun for cosmic inflation, the theory that the universe underwent exponential expansion in its first fraction of a second. If inflation happened, it would have sent ripples through space-time itself, primordial gravitational waves that left a distinct swirl-like fingerprint in the CMB's polarization. Experiments like BICEP and the Simons array are scouring the skies for this elusive signal, which would confirm not just inflation, but also a profound connection between quantum mechanics and gravity. The implications are staggering. Detecting these primordial waves would mean peering back to a time when the universe was a trillionth of a trillionth of a trillionth of a second old, a realm where the laws of physics as we know them break down. It could reveal whether our universe is just one bubble in an infinite multiverse, each with its own unique physical constants. And it might explain why the cosmos appears so finely tuned for life, because in a sea of infinite possibilities, we naturally find ourselves in a universe that allows us to exist. Yet the cosmic microwave background isn't just about the past. It's a roadmap for the future. By studying how these ancient fluctuations evolved into galaxies, scientists can refine their models of dark matter and dark energy, two of the greatest mysteries in modern cosmology. The CMB's light has traveled nearly 14 billion years to reach us, carrying echoes of a time before stars or planets, and in its whispers, we might just find the answers to where the universe is headed next. From quantum ripples to galactic superstructures, the cosmic microwave background bridges the smallest scales to the largest, connecting the universe's birth to its ultimate fate. And as we decode its secrets, we're not just uncovering the story of everything, we're learning how to read the universe itself. Astrobiology isn't just about hunting for little green men, it's about rewriting the very definition of life itself. Consider Mars, our rusty neighbor, where the Perseverance rover drills into ancient lake beds, searching for chemical signatures that vanished from Earth billions of years ago. Those rust-colored sands might hold fossils of microbial mats, relics from a time when Mars was warmer and wetter, but the real intrigue lies in the subsurface. Underground aquifers, shielded from harsh radiation, could still harbor extremophiles organisms thriving in conditions that would kill most Earth life. Imagine bacteria metabolizing perchlorates, turning toxic salts into energy, or fungi clinging to moisture in volcanic rock. These wouldn't just be aliens, they'd be proof that life is a cosmic rule, not an earthly exception. Then there's Europa, Jupiter's icy moon, where a global ocean sloshes beneath a frozen crust. Tidal forces from Jupiter's gravity keep that ocean liquid, possibly fueling hydrothermal vents like those on Earth's seafloor hotspots teeming with tube worms and chemosynthetic bacteria. NASA's upcoming Europa Clipper mission will map that hidden sea, measuring its salinity and even sniffing for organic molecules in plumes erupting through the ice. But Europa isn't alone. Enceladus, Saturn's sparkling moon, sprays geysers of water into space, offering free samples of its subsurface ocean. Cassini's fly-throughs detected hydrogen and silica, key ingredients for methanogens, microbes that thrive in Earth's darkest depths. To test these possibilities, scientists recreate alien hellscapes in labs. In Germany's Mars simulation chamber, researchers freeze bacteria to -50 degrees Celsius, bathe them in artificial Martian radiation, and watch as some not only survive but repair their DNA. Other experiments simulate Titan's methane lakes, where life might use liquid hydrocarbons instead of water, or Venus's acidic clouds, where airborne microbes could float like microscopic balloons. These studies reveal life's staggering adaptability and hint that we might be looking for life in all the wrong places. The discovery of even a single extraterrestrial microbe would shatter paradigms. It would mean life arose independently at least twice in our solar system, suggesting the universe is brimming with biology. But what if we find life that doesn't fit Earth's template? Silicon-based metabolisms, organisms with mirrored biochemistry, or creatures thriving in pure ammonia would force us to expand biology's rulebook. Astrobiology doesn't just search for life as we know it, it challenges us to imagine life as we don't. Now shift your gaze from icy moons and red deserts to the quantum realm, where the fabric of reality behaves in ways that defy intuition. If astrobiology explores life's potential diversity, quantum cosmology asks an even deeper question. How did the universe's fundamental laws make life possible at all? Quantum cosmology asks a question so profound it bends the mind. What existed before existence itself? Picture the universe squeezed into a space smaller than an atom, where the frenetic dance of quantum particles dictated reality. At these scales, the smooth space-time we know shatters into a seething foam of probabilities, where cause and effect lose meaning and particles blink in and out of existence. This is the realm where loop quantum gravity takes center stage, a theory proposing that space isn't continuous but woven from tiny, indivisible loops. Imagine the fabric of reality as a mesh of interconnected threads, each so small that a million could fit across a single atomic nucleus. In this view, the Big Bang wasn't the beginning but a big bounce from a previous universe's collapse, with these loops preventing the infinite density of a singularity. The implications are staggering. If space and time are granular, then the smooth cosmic expansion we observe today emerges from something deeper, like watching individual pixels blend into a seamless movie. This could solve one of physics' most vexing problems, the singularity at the heart of black holes and the Big Bang, where equations break down and predictions vanish into infinity. Loop quantum gravity offers an escape, suggesting these singularities are illusions, smoothed away by the quantum graininess of space. But how do we test such radical ideas? Cosmic archaeology provides clues. The cosmic microwave background, the afterglow of the Big Bang, holds faint imprints of the universe's quantum origins. Some theories predict subtle patterns in this ancient light, swirls or anomalies that could reveal whether space-time truly has a pixelated structure. Meanwhile, gravitational wave detectors might someday catch echoes from the universe's first moments, ripples carrying signatures of quantum gravity's effects. The hunt for these signals isn't just about the past. If quantum cosmology is right, then black holes, those cosmic shredders of information, might not be the ultimate dead ends we once thought. Their cores could transition into new regions of space-time, bridges to other universes or different epochs of our own. It's a dizzying thought. The universe's birth and its most destructive objects might be two sides of the same quantum coin. Now imagine peeling back another layer, not just of space but of time itself. If the universe emerged from a quantum state, could time be an illusion? an emergent property like temperature arising from the motion of atoms. Some models suggest that at the deepest level there is no before or after, only relationships between events. This would mean the arrow of time we experience, the relentless march from past to future, isn't fundamental, but a consequence of the universe's expansion and increasing disorder. The beauty of quantum cosmology lies in its audacity. It dares to connect the infinitesimal with the infinite, suggesting that the same rules governing subatomic particles might also sculpt the cosmos. And as we stand on the brink of new discoveries, from next-generation telescopes to tabletop quantum experiments, we're not just uncovering the universe's history. We're rewriting the story of reality itself. Next, we turn to cosmic archaeology, the forensic science of the universe, where ancient light and primordial elements become clues to deciphering the cosmos's earliest chapters. Cosmic archaeology turns the night sky into a time machine, one where ancient stars serve as fossil records, preserving the universe's chemical infancy. Take HD 140283, a star over 12 billion years old, drifting through our galactic neighborhood. Unlike younger stars enriched by generations of supernova, this relic contains barely any heavy elements, just hydrogen, helium, and traces of lithium forged minutes after the Big Bang. Studying such metal-poor stars is like cracking open a cosmic time capsule. Their compositions reveal how the first stellar giants, hundreds of times more massive than our Sun, seeded the cosmos with heavier elements through cataclysmic explosions. These primordial beacons don't just tell us what the early universe was made of, they show how it evolved from simplicity to complexity, atom by atom. Then there are quasars, the universe's lighthouses. These monstrous black holes, billions of times the Sun's mass, devour gas so furiously they outshine entire galaxies. But their true value lies in their light's journey to Earth. As quasar radiation passes through interstellar gas clouds, specific wavelengths get absorbed, leaving dark lines in their spectra like barcodes. Each line corresponds to an element: oxygen, carbon, iron, allowing astronomers to map how these materials spread across cosmic time. The most distant quasar yet discovered, J0313-1806, beams light from when the universe was just 670 million years old. Its spectrum captures the epoch when the first galaxies ignited, burning away the cosmic fog of neutral hydrogen in a process called reionization. This forensic starlight also exposes the universe's toddler years, the cosmic dawn. Radio telescopes like the Square Kilometre Array probe even further back, hunting for whispers of hydrogen from the universe's first 100 million years. These signals, redshifted to ultra-low frequencies by the expansion of space, could reveal how the first stars and black holes emerged from darkness. Now, shift focus from the distant past to an urgent present-day application: space's role in climate science. Satellites like NAS, a GRACE mission track Earth's shifting water masses by measuring microscopic changes in gravity, while others monitor deforestation, ice melt, and ocean currents with pixel-perfect precision. The same tools mapping quasars billions of light-years away also chart the health of our home planet, proving that cosmic exploration and earthly survival are inextricably linked. The same telescopes that map distant galaxies also keep a watchful eye on our home planet, turning space technology into one of humanity's most powerful tools against climate change. Picture satellites like Sentinel-6, orbiting 1,200 miles above Earth, armed with radar altimeters so precise they can measure sea level rise down to the millimeter. These unblinking sentinels have revealed that oceans are climbing 3.4 millimeters per year, a silent crisis captured from space long before coastal cities feel the floodwaters. But it's not just about tracking the inevitable. When NASA's GRACE mission detected groundwater depletion in California's Central Valley, it exposed unsustainable farming practices, prompting policy changes that slowed the crisis. From melting ice sheets in Greenland to shifting rainfall patterns in the Amazon, space-based observatories stitched together a planetary health report no ground network could match. Meanwhile, solar physicists monitor our stars' tantrums, predicting geomagnetic storms before they fry power grids or knock satellites offline. The Deep Space Climate Observatory, parked 1 million miles from Earth, acts as a solar storm early warning system, giving utilities precious hours to protect transformers from cascading blackouts. But the sun's influence runs deeper. By studying solar cycles, those 11-year ebbs and flows of sunspots, scientists can refine climate models, separating natural variability from human-caused warming. It's cosmic detective work where the stakes are nothing less than civilization's resilience. Then there's the fight against deforestation. Brazil's INPE agency uses satellite data to spot illegal logging in the Amazon, with resolution sharp enough to distinguish a single bulldozer's path. At night, instruments like VIRS detect the glow of wildfires in Siberia or Indonesia, tracking carbon emissions in near real time. Even air pollution becomes visible from orbit, as ESA's Copernicus satellites map nitrogen dioxide plumes over cities, revealing how lockdowns during the pandemic cleared skies almost overnight. The irony is profound. The technology we developed to explore the stars now helps us mend our planet. GPS guides precision agriculture, slashing fertilizer runoff. Solar panels born from space program innovations power homes with sunlight instead of coal. And when Hurricane Ian barreled toward Florida, GOES satellites delivered minute-by-minute forecasts, saving countless lives. This interplay between cosmic curiosity and earthly survival begs a question: what's next for humanity's relationship with the universe? As we harness space to heal Earth, we're also laying groundwork for an even grander chapter, becoming a multiplanetary species. The same climate science guiding us toward sustainability could one day terraform Mars, while asteroid mining might relieve pressure on Earth's dwindling resources. The line between protecting our planet and expanding beyond it is blurring, revealing a truth as vast as the cosmos itself. Our destiny isn't just written in the stars, but in how we bridge the gulf between the heavens and home. Interstellar travel isn't just the stuff of sci-fi, it's a scientific frontier where imagination collides with the harsh realities of physics. Take Alpha Centauri, our closest stellar neighbor at 4.3 light-years away. With current technology, a probe like Voyager would take over 70,000 years to reach it. That's longer than human civilization has existed. But here's the twist: we're not limited to chemical rockets anymore. Projects like Breakthrough Starshot are redefining what's possible. Imagine a fleet of gram-scale probes, each attached to a light sail thinner than a human hair. A ground-based laser array would blast these sails with gigawatts of power, accelerating them to 20% the speed of light. At that pace, they'd reach Alpha Centauri in just 20 years, beaming back images of any planets they find. It sounds like fantasy, but the physics checks out. Thermal management, radiation hardening, and laser propulsion are all areas of active research, yet the challenges are staggering. Interstellar space isn't empty, it's a minefield of cosmic rays and micrometeoroids. At relativistic speeds, even a speck of dust could vaporize a probe. Shielding solutions range from beryllium copper armor to self-healing nanomaterials, but the real breakthrough might lie in redundancy. Send thousands of probes and statistically, some will survive. Then there's communication. Transmitting data across light years requires lasers tighter than a pencil beam, with receivers on Earth the size of football fields. Breakthrough's team is already testing prototype sails in low Earth orbit, proving that the audacious can become the achievable. But what if we're thinking too small? For human travelers, the hurdles multiply. Radiation exposure alone could doom a crew before they reach another star. One radical solution: generational ships, self-contained arcs where multiple generations live and die en route. These wouldn't be sleek starships but floating ecosystems, recycling every molecule of air and water. Artificial gravity might come from spinning habitats, while closed-loop agriculture sustains the population. The psychological toll: uncharted territory. Confined for centuries, would social structures collapse, or would new forms of culture emerge? Experiments like Biosphere 2 hint at the fragility of closed systems, but they also prove the concept isn't pure fiction. Alternatively, ditch the humans entirely. AI explorers could withstand the centuries-long journey, their minds unburdened by mortality or loneliness. Imagine a robotic von Neumann probe landing on an exoplanet to mine materials and build copies of itself, fanning out across the galaxy like an unstoppable tide. The ethics are murky. Should we seed the cosmos with our creations before we fully understand their implications? And what if another civilization intercepts them, interpreting our probes as a threat? The truth is, interstellar travel demands more than engineering. It forces us to confront our place in the universe. Are we destined to remain a single-planet species, or will we become the architects of our own cosmic diaspora? The answers might lie in technologies we've yet to invent, or in re-evaluating what it means to explore. One thing's certain: the stars aren't just points of light. They're invitations to push beyond the limits of the possible, to write the next chapter of humanity's story among them. The constants of nature read like a cosmic recipe, one where even the slightest tweak would render life impossible. Take gravity, for example. If it were just a fraction stronger, stars would burn too hot and fast, collapsing into black holes before life could emerge. A smidge weaker and stars might never ignite at all. The same goes for the strong nuclear force holding atoms together. Adjust its strength by even 1% and carbon, the backbone of organic chemistry, couldn't form. These razor-thin margins aren't limited to physics. The universe's expansion rate, the mass of electrons, even the density of dark energy, all seem calibrated with eerie precision to allow galaxies, planets, and ultimately, conscious beings like us to exist. This uncanny fine-tuning is the heart of the anthropic principle, the idea that the universe's properties must be compatible with the observers who study it. But here's where the debate ignites. Some argue this apparent fine-tuning points to deeper design, a cosmic architect setting the dials just right. Others counter with the multiverse, a vast ensemble of universes, each with different constants, where we simply find ourselves in the rare one where life can arise. Imagine a cosmic lottery with infinite tickets, each representing a universe with randomly shuffled laws. Statistically, a few would hit the jackpot, and we're living in one of them. Yet the multiverse isn't a tidy escape hatch. For one, it's untestable by definition. If other universes are forever beyond our reach, how do we confirm they exist? And if every possible universe exists somewhere, does that dilute the meaning of our own? Philosophers and physicists clash over whether invoking infinite universes solves the mystery or merely kicks it down the road. Meanwhile, alternative explanations simmer on the scientific stove. Could the constants evolve over cosmic time, settling into life-friendly values through some unseen mechanism? Or might a deeper theory, a final theory of everything, reveal that these numbers aren't arbitrary but emerge inevitably from fundamental principles? String theory, for instance, suggests the universe's parameters could be locked in by the geometry of hidden dimensions. What's undeniable is how this debate reshapes our cosmic perspective. Whether through divine intent, multiverse statistics, or undiscovered physics, the anthropic principle forces us to confront a humbling truth. The universe isn't just a random backdrop. It's a stage meticulously set, and we're the audience finally waking up to the wonder of the performance. Now consider this: if the cosmos is so finely tuned for life, what does that imply about our role within it? Are we accidental witnesses, or does our ability to ponder these questions hint at something deeper? The answer might not lie in equations alone, but in the very act of seeking. A universe not just built for life, but for understanding itself. Long before telescopes and satellites, the night sky was humanity's first classroom, a glittering textbook written in constellations. Ancient Polynesian voyagers navigated thousands of miles across open ocean by memorizing the rise and set of stars, their canoes guided by celestial waypoints like the Southern Cross. Meanwhile, halfway across the world, Babylonian astronomers etched precise planetary movements onto clay tablets, laying the groundwork for modern mathematics. These weren't isolated pursuits. They were threads in a global tapestry of curiosity, woven by cultures who saw the heavens not as distant lights, but as guides, calendars, and storytellers. The same stars that inspired Stonehenge's alignment also guided Egyptian farmers planting crops along the Nile, proving that the cosmos has always been more than a spectacle. It's the spark that unites human ingenuity across continents and centuries. Fast forward to today, and that spark has ignited a wildfire of discovery. The Hubble Space Telescope's breathtaking images of nebulas didn't just advance science, they transformed public imagination, turning abstract equations into shared cultural touchstones. When the Event Horizon Telescope revealed the first image of a black hole's shadow, it wasn't just a scientific milestone, it was a moment of collective awe, trending globally on social media alongside cat videos and memes. This is the paradox of cosmic exploration. The farther we reach into the void, the more it reflects our deepest human connections. Space agencies collaborate across geopolitical divides, with astronauts from rival nations sharing meals aboard the International Space Station, their unity a silent rebuke to earthbound conflicts. But the cosmos doesn't just unite us, it challenges us to think bigger. The Apollo program's legacy isn't just lunar footprints. It's the countless spin-off technologies, from MRI machines to fireproof materials, born from solving space-bound problems. The quest to build lighter spacecraft led to breakthroughs in water filtration, while satellite technology now tracks endangered species and monitors climate change. Even the humble CMOS sensor in your smartphone camera traces its roots to NAS, a need for compact, low-power imaging in space probes. What makes this celestial curiosity so powerful is its refusal to accept limits. When Einstein's equations suggested black holes, scientists didn't dismiss them as mathematical quirks. They built telescopes to find them. When the Voyager probes ran out of planets to explore, they kept going, becoming interstellar messengers carrying golden records of human culture. And when the James Webb Space Telescope's mirror segments needed perfection, engineers invented entirely new ways to polish and test them: the common thread. A stubborn belief that no question is too grand, no frontier too distant. As our celestial journey comes full circle, remember this: the stars have never been passive bystanders. They're collaborators in the human story, pushing us to invent, explore, and above all wonder. Whether through a child's first telescope or a Nobel-winning astrophysics breakthrough, that spark of curiosity remains our most celestial trait. And as long as we keep looking up, the universe will keep surprising us. We've journeyed through the heart of black holes, danced across the theoretical landscapes of multiverses, and marveled at the staggering diversity of alien worlds, each revelation peeling back another layer of the universe's grand design. But here's the beautiful paradox. Every answer we uncover doesn't simplify the cosmos. It deepens the mystery. The universe isn't just a static stage for human discovery. It's an active participant, challenging us to think bigger, dig deeper, and rewrite the rules of what we thought was possible. Consider the humble act of stargazing. When you look up at Orion's belt or the shimmering haze of the Milky Way, you're not just seeing distant lights. You're witnessing the aftermath of cosmic collisions, the birth cries of newborn stars, and the gravitational tango of galaxies locked in an eternal dance. That flicker of a star might be its final gasp, a supernova's light reaching us centuries after the explosion itself. The darkness between them, not empty at all, but seething with dark matter, quantum fluctuations, and the invisible threads of gravity weaving the cosmos together. This isn't just science, it's a story we're all part of. Every time a child points at the moon, every time a researcher crunches data from a distant exoplanet, every time an artist captures the swirl of a nebula on canvas, we're adding to humanity's collective conversation with the universe. The questions we ask today: could life thrive in the icy oceans of Enceladus? Does quantum entanglement hold the key to faster-than-light communication? Might seem like science fiction, but so did black holes and gravitational waves just a few decades ago. And that's the most thrilling part. The next groundbreaking discovery could come from anywhere. Maybe it's lurking in data from a telescope yet to be built, or hiding in the equations of a student scribbling on a chalkboard right now. The cosmos doesn't discriminate. It reveals its secrets to the curious, the persistent, and those unafraid to question the impossible. So as you step outside tonight, let the stars remind you of something extraordinary. You're not just an observer of the universe, you're made from it. The carbon in your bones, the iron in your blood, all forged in the hearts of long-dead stars. That connection isn't poetic license, it's scientific fact. We are quite literally the universe experiencing itself. The journey doesn't end here. Hit subscribe to join us as we chase the next cosmic mystery, and drop a comment below. What celestial wonder keeps you up at night? A supermassive black hole's appetite, the eerie silence in the search for aliens. Whatever it is, keep looking up, keep questioning, and remember, the greatest discoveries often begin with a simple, awe-inspired "what if?" The cosmos has spent 13.8 billion years setting the stage. Now it's your turn to explore it.